Welcome back everyone for the second part of my Proxon MF70 CNC conversion. If you haven't watched the first part where I did the Z-axis, go have a look right here. What is this work of art, you might ask? It actually looks kind of like Proxon's own official CNC conversion kit. In reality, it has nothing to do with that. Well, let me show you. Yes, this is a planetary drive. I've created it myself, starting from a model I found on Thingiverse. Somehow I thought that I would be able to get a bit more torque from the NEMA 17 stepper motor and avoid all the skipped steps that I sometimes got. Long story short, the precision was garbage and all the torque I thought I would get from the 5-to-1 reduction was lost in friction and binding between the gears. I'm almost sorry for all the high quality grease that I wasted to pack the gearbox. But before we proceed, if you think this XY table looks ginormous, indeed it is. Story is, when I bought the milling machine, it came with this engraving pantograph. Very beautiful piece of equipment, nicely crafted, useless in practice. With all the flex and play in the mechanism, it just never worked. And since I didn't pay for it from my own pocket, I had no trouble cannibalizing it for the bigger table, especially in the Y track, which is just ridiculously small in the original model. I now get 83 millimeters of Y travel instead of the original 46 millimeters. Now, back to our project. I would like to follow the same principles I used on the Z-axis, meaning the stepper motor becomes the fixed point of each axis. The lead screw is coupled rigidly to the shaft of the stepper motor. Make my own 3D printed nut to replace the original one which is allowed to rotate in its seat. Here is an anti-backlash system which is available on Thingiverse. It uses two classic nuts separated by a spring. I've tried it and didn't get much luck with it. To get a meaningful anti-backlash effect from the spring, the force it exerts on the nuts makes rotation difficult. I even tried my own variation with two nuts made from Teflon, which you saw in the previous video when I straightened the lead screw. Well, it still doesn't rotate easily. This system requires you to make a cutout in the original cross carriage. Since I already did this, I'm going to use this same model as the starting point of my own version. As I did with the Z-axis, I will 3D print the part and tap the hole myself for the lead screw. Mind you, the lead screw for the Y-axis is left-handed, so I had to buy a specific tap for this part. Now, motors. As I said, this will be the fixed point of each axis. As I did on the Z-axis, I'm replacing the wave washer inside the motor with a solid one which I 3D printed to the exact right thickness. And yes, the play was different for each of the three motors. As I did with the Z-axis, I'm using the exact same coupler which I 3D printed to make a rigid connection between the motor shaft and the lead screw. It looks like it's not going to be easy. I was going to continue the project in this direction when, look what the cat dragged in. These are 8mm Acme lead screws which I ordered from eBay a few weeks ago and they just arrived. They are 1mm in pitch, single lead, and Since I'm going through all this effort, I thought perhaps I should do a more thorough upgrade and replace the original metric lead screws with trapezoidal ones. Just a quick side note about the advantages of a trapezoidal thread profile over the metric thread when used in a lead screw. The forces transmitted between the lead screw and the nut follow a line perpendicular to the surface of contact between the two. The useful component of this force along the direction of travel, in green here, is proportional to the cosine of half the angle of the thread. So in the case of a metric thread, more of the force is transmitted laterally and the useful component is smaller than in the case of the trapezoidal thread. So a small advantage to be gained here, and with the NEMA 70 not being the beefiest of stepper motors, every bit of help counts. Now, all I need to do is find a trapezoidal TA tap and continue the project. Now, all I need to do is make a TA tap and go on with the project. Once cut to length, I can use the leftover from the lead screw to make my own tap. I saw this in a few videos on YouTube, and since it will be cutting plastic, it shouldn't be too difficult. There are better ways of doing it, I'll admit. I just have to cut the gutters along the length and some relief at the front, plus a little bit of cleaning, and it should work. It doesn't look great, but let's see if it does the trick. Well, this was harder than it looks on the video. A lot of back and forth needed, I suppose because of the cutting teeth which weren't too well defined, but it turned out alright. Fixing the new cross nut to the carriage is not very obvious. I had to mark the holes and make them a bit larger to allow for a few small adjustments. In the end, the alignment is made by trial and error. It took me 3 tries to get the 2 screws aligned with the final position of the motors. Time to fix the lead screws to the motors. I've designed new couplers for the new 8mm diameter of the lead screw. Given that the lead screw is threaded on all its length, I have some trust issues when it comes to using just 2 set screws to hold everything together. So I'm going full overkill and using some epoxy glue inside the coupler. The bridge between the motor and the table is made in exactly the same way as for the Z-axis. The only difference being that it will have the appropriate interface to be mounted on the X and Y axes respectively. Once printed, they can be installed on the end of each axis. Same with the motor, which will be mounted onto a separate plate and then installed on the bridge we designed earlier. It seems to move without any trouble. Time now to install it on the column base and complete this build. Let's give it the old micrometer test and see what's what. You will have to excuse the nature of my fixed point for this part. It was just the heaviest object that I had lying around. So, between 0.02 and 0.03 millimeters, along with some other imperfections which I suspect might come from the table itself and the ever-present dovetail track. It looks like all this effort was not in vain. I'll put the files on Thingiverse in the next few days, maybe do a small video to wrap things up. Thank you very much and hope to see you soon for another video.